We're going to look at a practice problem on the work energy theorem. This problem reads, a 50 kilogram figure skater is gliding along the ice heading due north at 4 meters per second. The ice has a small coefficient of static friction to prevent the skater from slipping sideways, but the coefficient of kinetic friction in the direction of motion, the sliding friction, is 0. Suddenly, a wind from the northeast, 45 degrees, exerts a force of 4 newtons on the skater, but the skater continues to move north. What is the skater's speed after gliding 100 meters in this wind? And what is the minimum value of the coefficient of static friction that allows her to continue moving straight north? All right, so let's look at how this problem might be approached thinking about work and energy. So let's draw our picture. I'm going to do sort of a top-down view. Here is the skater, and she's going to be traveling north at 4 meters per second. When a wind, it says from the northeast, so the wind is coming from this direction, so this is the force of the wind, and that was equal to 4 newtons, yeah, 4 newtons, and that wind is acting at an angle of 45 degrees. So that's the same angle as this, if you're visualizing it from the positive x-axis. So there is our situation. Now, this ice skater is experiencing a force. That wind is doing work on the ice skater. If the wind is exerting a force, it's doing work on that ice skater. And we want to keep in mind that the net work done on that ice skater is equal to the change in kinetic energy. So let's look at the net work. Now we're only going to look at that net work done in the plane of the motion. So remember, work is equal to the force times the distance, and that force is the parallel force. So this translates into that force d times the cosine of the angle, where the cosine of the angle is between the force and the displacement. All right, so what is the, first of all, the component of the force that acts along? This is the force that's doing the work. The component that acts along the displacement is actually in the other direction. There we go. All right. So that's the magnitude of the force doing the work. So our cosine is, this angle is not our 45 degree angle, right? So it's between the force and the displacement. So it is also 45 degrees, but we want to keep in mind that this component is the sine. The force equation typically is that cosine, but again, there's multiple ways to do this, right? You can use that interior angle and make sure you're looking at the right component, or you can use the angle that we've done before. Okay, so we're going to, because I've chosen to use the interior angle idea, we're going to keep this just as the component of the force in the direction, in the dimension of the displacement. All right, so what work is being done by that force? Well, the force is 4, so the force that's parallel, to the displacement is the opposite, 4 times the sine of 45 degrees. So 2.83 newtons is the force acting on that figure skater. So if the force acting on that figure skater is 2.83, we know that that figure skater is going 100 meters, I think. Yep. So 100 meters. So the work being done by that force is 2.83 times 100 meters. And we get 283 joules of work being done by that force. It's working against the motion, so it is a negative work. So it's working against the motion. Right, now using that information, we can look at the kinetic energy. So we have the work net, we said, was equal to the change in kinetic energy. So that's equal to the final kinetic energy minus the initial kinetic energy. We are interested in how fast the skater was going after gliding in that wind, so that's our final kinetic energy. So it's going to bring the initial kinetic energy over to the other side. So we have the work plus the initial kinetic energy is equal to our final kinetic energy. Then we have the work plus 1/2 the mass times the initial speed squared is equal to 1/2 the mass times the final v squared. So our work net was minus 283 joules plus 1/2 the mass of the skater was given to us at 50 kilograms times the initial speed, which was also given to us at 4 squared, is equal to 1/2, still the mass of 50, times our final speed squared. So we have minus 283, 25 times 4 gives us plus 400, I should have been able to do that in my head, plus 400 equals 25v final squared. So 400 minus 283 divided by 25, we get 4.68 is equal to the final velocity squared. And when I take the square root of that, we see that v final is 2.16 meters per second. So 2.16 meters per second after that skater experiences the wind for 100 meters. All right, so really efficient process using the idea of that wind is doing work on that skater, that work is changing that skater's kinetic energy, and we can use the work energy theorem to solve that problem, as opposed to doing a force analysis, finding the acceleration, and then doing kinematics. So it's a lot more efficient, remember, when we use work and energy. All right, the second part of that question says, what's the minimum value of the coefficient of static friction that allows her to continue moving straight north? Okay, so in this case, the coefficient of static friction is preventing the skater from moving right or left. So we also know that we have a force equilibrium problem. So we could do this pretty efficiently looking at force equilibrium. So if we look at the horizontal forces acting on the skater, we know that we have the component of the force of the wind, and we have the frictional force. So we're going to look at this in terms of that force analysis. So this tells us that and then, of course, we have to have the normal force acting up on the skater and the force of gravity that acts down. So the wind is producing a horizontal force. This is now looking at the plane of the skater. Okay, so the wind is pushing horizontally on the skater in that plane. We have the frictional force acting on that skater, the normal force acting on that skater, and the force of gravity. All right. So how do we find this coefficient of static friction? Well, we need to look at our relationships. So here we divide our horizontal and vertical forces. We have our horizontal force, friction, nothing happening vertically. We have our normal force. We have our horizontal component of the wind in the opposite direction in that plane. And we have the force of gravity. The sum of these forces is equal to 0. The sum of these forces is equal to 0. We're not changing location in that right or left dimension. So we have the frictional force minus the force, horizontal component of the wind is going to equal 0. So we know our frictional force is the horizontal component of the wind. So given that, we have 4 times the cosine of 45. And we've done the sine and the cosine of 45 are the same. So our horizontal component of the force of the wind is equal to 2.83 newtons. And it's acting to the right. I'm sorry. Yeah, the frictional force is acting to the right. And we know that that frictional force is equal to mu times n. And we're interested in what that mu is. So we need n, and we can use that we can get that using our vertical components. So the normal force in this case does equal the force of gravity. The object is not translating up or down. And so that is 50 times 9.8. And so we have a normal force of 490 newtons. So mu is equal to 2.83, divided by 490, 0.006, or 58. All right, so there's a little bit of a trick on this one, because we have to sort of think about the motion along the plane, the force acting along that plane. It tells us it's acting along that plane. But then to do the force analysis and get friction, we have to consider the normal force acting, because friction is dependent on that normal force. We have to sort of shift the plane and look in that vertical horizontal dimension. So we sort of have a three-dimensional thing going on here. We have the plane, and then we have its orthogonal component. That gives us that normal force and the force of gravity. So work energy, very straightforward on that first part of the problem. And then looking at a force analysis, remind us some of that other stuff. But really thinking about what is the direction of the frictional force, and then what is the opposing force, in this case the wind, and what component does that look like. All right. Good job.